This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So two announcements. If your tutorial session is Friday, and you need to attend it this week, because next Friday is a university holiday, so we move we switch around. So you will attend this Fridays for the tutorial 3, and then the rest sessions will be held as scheduled next week. All right. So, and the assignment is due on the coming Monday. So make sure you already started working on that. So in the last lecture, we discussed, we briefly introduced the 3 heat transfer modes and the rate equations describing the heat transfer rate through or via each of the modes. And then we discussed the problem of multi-mode heat transfer. So that's where you will see the problem in the next tutorial sheets there. And today we are going to focusing on the conduction. So we will use about 2 weeks to finish this topic. The thermal conduction, that's the topic here. So some of the physical understanding of this phenomena, in terms of the conduction or thermal conduction, we said that the conduction requires certain medium in order to happen, and that medium is basically it's a medium so that the energy can pass through. The thermal energy can go through. So without that medium, the heat cannot be transferred in the form of the conduction. It can happen in terms of the radiation if it's not blocked of the radiation waves or the passage, but the medium is the requirement for conduction to happen. So in terms of the physical understanding, we can write the conduction is the passage of thermal energy through a medium, and this passage happens microscopically is due to the particles, atoms or electrons in the medium. So if we're focusing on the microscopic level, that is the energy being transferred from atom to atom in order for this kinetic energy, or the microscopically the kinetic energy being transferred from one place to another. So let's finish this. Through the medium via microscopic So by particles, I refers to the atom, molecules, or electrons. Right. So, for example, if we have, let's say, a medium, which is solid for this case, right? Let's say this is a wall as a solid. A solid essentially is many particles, atoms being compacted together, right? So if I can draw some really rough approximation of the structure, on the surface you have a layer of atom or layer of particle, and then you have a second layer and a third layer, etc. Right, and then you have another layer on the other surface. Right, so when thermal energy come in, or you can say when heat come in. So let's say if this side is high temperature, so the T1 and the T2 and the T1 is higher than T2, right? So basically what it's saying is that when the heat is coming onto this surface, the first layer of atom, let's say atom, then it will get excited. So at the microscopic or at the molecular level, the energy is not continuous. The energy is discretized, so which means it's coming as a packet. For example, for this case, the energy is coming as a phenomenon called the phonon. So similar to the photon, but now it's in the form of thermal energy, which is similar to the sound that hit surface. But anyway, the energy in terms of the thermal energy coming here, which will get the first layer of atom excited, then will start to move because it receives energy. It tries to move at a higher kinetic energy at the microscopic level. Then when it gets excited, it will hit the next layer of atom, right? And then the next layer will get excited as well, and then the third layer will get excited as well, right? So because they are packed together, so the thermal energy will be transferred due to the microscopic motion of these particles, and eventually it will reach here. So in this case, you can certainly consider that the heat transfer or the energy transfer due to the collision process is not elastic, which means along the passage that the thermal energy being transferred, not all the thermal energy at this surface will be transferred to the other surface. So some of them got lost just because the collision between the atoms is not 100% efficient, right? The collision cannot transfer all the energy there. So in the process, the medium is got heat up. So all the atoms will keep certain amount of the energy. So by another words, the temperature will go gradually from one side to the other. So this side is hotter, this side is colder, and the area or the state in the middle will be somewhere in between these two extremes. That's just because the energy transfer process is not 100% efficient. So that will determine a property called thermal conductivity, which is a K. So thermal conductivity, you can consider that's something to describe how effectively, how efficiently the energy can be transferred across a medium. if the energy loss is less, which means the energy can be more effectively transferred to the other side, right? So in this case, the K is a large value, higher thermal conductivity, and in that case, the temperature of the T2 and the T1 will be relatively close if we consider the input energy as the same. For the same amount of input energy, with a larger K, the T2 will be closer than T1. But if you have a poor conductor, which means you have a smaller K, then there is a lot of energy will got lost along the way, which means energy transfer process is not effective. Then you will have a large difference for the T2 over T1. Right, so that's the some understanding in terms of what actually happened for the conduction. But I should say this is more for the non-conducting or maybe non-metal solid. We can consider something like this in terms of how the conduction happens. So if it's a gas or fluid, right, we can apply the similar concept, except when you have a gas, the density in the medium is a lot smaller. Right? In general, it's the order of 1,000 times smaller. So in that case, the energy transfer is not efficient, more efficient or less efficient. If you have a gas which have a density is 1,000 times less, is the energy transfer will be more efficient or less efficient, or more effective or less effective? Less effective, because there is a lot of void in the space, right? So for one particle to find another particle to transfer energy, that takes the opportunity for that to happen is a lot lower. So energy is transferred much less effectively, and that's why the gas, the thermal conductivity is much lower compared to solid in general. So similar for gas, but with much lower particle density. Right. So we can use this schematic to understand how conduction happens through gas or through non-metal solid. So the things are different from metal. So if we have a metal, the process is not necessary. I mean, this still happens, but it's not the dominant way that the thermal conduction happens. So for metal, you have free electrons. So that the free electron is a more effective because for metal the electron is not bind so tightly with the atom, right? So the electron can move relatively freely, and when you have a particle can move more freely, that's more efficient or effective in terms of the energy transfer. So for metal, I should say the heat conduction is more happens. Heat conduction primarily via the movement of an electron. So for this reason, there is a general rule of thumb saying that a good electric conductor in general is a good thermal conductor. So certain material, for example, copper, is a very good electric conductor. So its electrical resistance is quite small, and by the same reason, its thermal resistance is also small, which means it's a very good thermal conductor. So that's a rule of thumb. And we can say that that's mainly because the mechanism there is due to the process happens both via the electrons. But in the thermal conduction, you don't have current, right? The thermal conduction is via electron, but the electron is still localized. You don't have a flow of the electron across the medium. So that's why you don't have electric current. So that's basically two types. Solid non-metal will be via this type of mechanism, and the metal that will mainly through the electrons. There is one special compound or one special material which is not metal but has very high thermal conductivity, which is a diamond. So if you're looking at the table of the K value for different material, diamond is always way at the top. So it's a much higher thermal conductivity compared to the best metal there. And the reason for that is this is a similar concept as here. But for a typical metal or typical non-metal solid, all the particles, they are packed together quite loosely. There is no structure, essentially. So the energy passage or energy transfer basically rely on some random collision from one layer to the other. But the diamond has a very rigid or very ordered structure. So if I can draw something to approximate, diamond is certainly is a crystal. So it has a very ordered structure. So each atom is located in the one of the nodes there. And the bonding between each of these two atoms are very strong. So they are very tightly connected together. So because of this structure, when you have excitation coming from one side, because of the strong bonded atoms, the energy hit this atom will be directly felt by the other atom on the other side. So you can consider this just like a rod. You hit one side, then the other side will directly feel the force. So that's just because the special structure of the diamond. So this is a diamond that has a very ordered and regular atomic structure. To make it a very efficient to conduct heat. So the K is much larger than metal. So in fact, this has been commonly used as a way as a measure to judge whether the material is metal or is diamond or not. So just by appearance or just by looking, sometimes it's difficult to judge whether that piece of glass is a diamond or not. But by measure its thermal conductivity, you can directly tell that. So that's being used as a way to tell it's a real or if it's a real diamond. All right, so that's some physical understanding regarding the conduction. In terms of the rate equation, let's say a few words about the things related to the calculation. So the rate equation that we showed last time, that's called Fourier's law. So that's the rate equation of conduction. So for that, we said the heat transfer rate can be written as the heat transfer area, product heat transfer area, the thermal conductivity of the material, and temperature gradient. So in the more rigorous form, we're using a differential term, the temperature gradient there, and then we have a minus sign in front of it. So this is a Fourier's law. So sometimes you can move the area to the other side, then you have the heat flux. So Q double prime equals to K times the temperature gradient. All right. So this is a pretty relatively straightforward law in terms of conduction. So if we're looking at what each of this term, right? So if we have the temperature there as T1 and temperature there as T2, right? So this law says that the heat transfer rate, which is by nature, we are going from this way there. And if we define this as 0 and along the heat transfer direction, we have the x coordinate, right? So this one saying that the heat transfer rate, which is a watts, equals to the area. What is this area? That's the area of this one, or this one. The area of this. So that's quite important because later on when we're talking, discussing different type of problem, we will see many areas. Sometimes they can refer to different area. So be clear to yourself what area the equation refers to. That's a very important one. So this area is the area normal to the heat transfer direction, right? We know the heat conduction is always, or the heat transfer always goes from the high temperature to low temperature. And this negative sign there actually is to correct the heat transfer direction so that we constantly have a positive value. So if you're looking at why we have a negative sign there is the heat transfer is going from the high temperature to low temperature, so this dt is always negative, right? Always negative for the heat to be transferred. And if we define the x as the direction of the heat transfer direction, then we will have a negative value just because of that. And the rest term are always positive, so we need a negative sign in order to correct it so that we have a positive direction to be consistent with the actual direction. So that's negative sign just because or due to heat transfer from hot to cold. All right, so then this temperature gradient term. So that's basically is a local value, unless you have a condition that this gradient can be written as a constant. For example, if I have a linear temperature distribution, then this one can be a constant. But in general, that's a local value. And this K is the thermal conductivity that we mentioned. And that's the material property. That's quite important to recognize because as a material property, we can somehow determine how much it is. Because as long as this material is known and its composition, which is forming this material, is uniform, then we can determine what's the value of its K. So this is basically is a given. If you know the material, you just go to the literature and to find the one. So this actually greatly simplifies the problem. So I have a table which is showing the typical K value for common materials. So here you can see that, as we said, diamond is the wear at the top. So it's nearly 6 times higher than the best metal conductor, silver. And copper and gold, aluminum, they are also good conductors, and they are also good thermal conductors and also good electric conductors. And a poor conductor, including air, which is gas, and the glass fiber, and helium, which is another gas, and water is also a poor conductor. You can see their value is several order of magnitude lower than metal. And a poor conductor is not saying it's useless. Right? So when we study the heat transfer, it's not necessarily saying a good conductor is a useful thing and poor conductor is not useful. Because a poor conductor, you also always have a situation where you want the heat transfer to not happen or happen as slow as possible, which means insulation. Right? In that cases, you want to be using this poor conductor to prevent the heat transfer to happen. So that's the K value, which is at the room temperature. The K value can be a function of temperature. So which is showing the plot here. This is from the lecture notes. So you don't need to take a photo here. So this one is showing that the K value for different material as a function of temperature. For most metals, you can see they are going down. But even they are going down, their value is very high. And certain material, for example, for I don't have air here. Yeah, for air in general, its thermal conductivity is going up with temperature. But overall, because the temperature temperature difference we're dealing with in the problem is not very large. So here you're looking at like one division is corresponding to 100 degrees C. So if the temperature difference is not very large, the K value change is not significant. So in many cases, we treat them as a constant. So that's a reasonable thing. But if the problem is saying that the K needs to be treated as a function of temperature, then certainly you want to follow that. All right. So the material property, we should say the generally known and can vary with temperature as a weak function. All right, so that's just a few words about the Fourier's law. So this law, as said, is pretty straightforward. And when we study the conduction, heat conduction problem, we using this law, and the primary goal when we study the conduction problem is to figuring out across the conduction medium what would be the temperature distribution. So here, for this case, for example, if we only consider one direction of the heat conduction, we want to know along the x direction, what's the temperature distribution along there. So for other cases, if we have to consider the conduction through different directions, then we have to consider multiple, the heat conduction through multiple directions, which means the temperature is not necessarily, temperature definitely not a function of the temperature, a function of x, can be a function of y, and the problem is not necessarily static, which means the whole medium can conducting heat and at the same time it can absorbing heat. So that's basically what the conduction problem is dealing with. I want to find out what's the temperature distribution for a conducting problem. And based on that, applying this law, we can know how much heat is transferred due to the conduction. So that's the next topic, that we want to derive a general equation so that we can know what's the temperature distribution in a conducting medium. So I should say we want to know the temperature distribution in the conduction medium and the heat transfer rate for any type of heat transfer mode, we want to figure out what is the heat transfer rate. So that's no problem. And particularly for the conduction problem, we want to know what's the temperature distribution within the medium. So that will require us to derive an equation called the heat conduction equation. So we derive the most general form, and in deriving this equation, actually it's a good practice in terms of study thermal and fluids problem. So here, the procedure I'm taking here will be used in multiple times later on. So following the method that we described last time, we will first we will select a control body, then apply the first principle, which for this problem is the energy balance, and then bring in the rate equation, then obtain the rate equation, then we have to do the integration to get that equation and solve that equation, solve the problem. Right, so it's a good practice of the a general thermal fluids problem you will see multiple times later on. So in order, so let's say now I have a volume for the conduction to happen. It's not necessarily a cubic, but I just draw it. So we have a volume like this, which is conducting heat. Let's say the heat is coming from that direction. And we have the medium, which itself is generating heat. It's not only a conductor, but it also is generating heat at a certain rate. So the Q dot stands for the heat generation term, and we said its dimension is watts per meter cubic. So this one is watts, right? The heat transfer rate. And then the problem is not it's necessarily one-dimensional, but it's a three-dimensional problem. So let's say this is x, y, and z. So a three-dimensional problem happening in this, let's say, in this medium. So we want to decide what is the temperature distribution. All right, any point in this medium, what is the temperature as a function of x, y, z, and as a function of time. So it's not necessarily a steady problem, but you can have energy change or internal energy change within the medium, right? So it's a pretty general problem we're dealing with here. The first step is to select the object so we can apply our first principle. And in this case, we want to know the distribution. And what we do is we're starting with differential control volume. Because if we select the whole thing as a control body, there is no much information we can gain in terms of the local value inside there. So in order to find local value, we want to select a differential control volume. So let's say I select a slice of this control volume of this medium as my control volume, and that one is along the x direction. So if I call this area as my AX, the area which is normal to the heat conduction on the x direction, right? So I have this one has a thickness of infinite small dx, and it has a location of x and x plus dx, right? So that's our control volume. Then we apply our first principle, which is energy balance to this body. And here we consider, again, the conduction problem only. We have conduction. We consider the heat transfer or conduction through the x direction for the first part. Then we can do the same for the other directions. So now we consider along the x direction, we have the Q conduct at the x location, and then the Q leaving the control volume at x plus dx location. That's basically the in, out, right? Then we apply the energy balance. And energy balance, we said we've not necessarily using the first law. The first law is something derived based on the heat engine, but we apply the general balance equation, which is in plus the generation equals out plus change. the storage or the change of the system. So that's the most general general conservation equation. And here we apply to energy. It can be applied to mass, momentum, or species. So if we do that, and you can see, if you apply it to a system where the first law is derived, this equation is always there. You just there just have certain cases which is making the equation even simpler. So here, if we consider the energy in terms of conduction, that's only this term. Again, once we select the control body, we stick to it. Right? Don't jump here and there. Once we select the control body, we're looking at what's energy getting into that control body. So in that case, that's only this Qx. That's energy energy generation. Do we have energy generation here? Yes, the Q dot and the Q dot is just energy per volume, right? We need to times the volume term in order to balance. Here is just the watts, right? We need the watts in order to be added together. So we need to control the volume. The volume is this control volume, right? And the control volume we can write in terms of the AX, the area, times the DX, which is the thickness. All right, so that's our gen. And then the out is a QX plus DX. That's no problem. And the change, so if we consider the temperature of the control volume changes with respect to time, we need to consider that term. And that term, how do we express it? Basically, it's the internal energy change with respect to time. Internal energy is any idea? Yeah, C dt, CV, CP, it doesn't matter here. Yeah, and yep, MC dt. Yep, very good. So we need a term like MC dt term there. That represents the internal energy as a change, and we need to deal with the time here because everything here has is per second thing, right? So let's say MC dt. Let me bring in the volume. So we have the density, we have the volume, which is AX dx. Then the C specific heat. So for solid, CP, CV are basically the same. And then we have the temperature, which is partial T, partial T. So that's the internal energy change, or we can consider as a storage, right? So this is a very important first step. That's the first principle in terms of the energy balance. Then we can move on from there. This is the very first step, and that's, if you get this wrong, everything following will be wrong, right? If you get this part wrong in your exam problem, then you won't get much points for that problem. So that's the first step. Then the next step, basically, I will simplify the terms. If I can write this as the heat flux term times the AX, and this one is written as the heat flux term X plus dx AX. right? And then I divide all the terms by ax as well as ax times dx for all the terms. And by doing that, I move this x plus dx term to the left-hand side of this equation. Then I will have the qx plus dx double prime minus qx double prime dx. Move this term to the left-hand side. And then this q dot will just by itself. And then I have the rho c partial t there. Right? So this one I can further simplify. And what I'm going to do here is, again, something I'm going to use a few times later on, and you want to remember it very well. So if you're looking at this term, this is a small change in terms of heat flux across the dx, then divided by the dx. So this term, if you remember how when you study calculus, how a differential is defined, you will recall, if you have when you study something if you have a function f plus dx minus fx corresponding to these two, and divided by dx, and when you have the dx approaching 0, this equation is equals to, this expression is equals to assume it's a the fx is continuous and differentiable. This will give you the, based on the definition that you learned from your calculus, probably very earlier stage, that one will equals to the differential of the fx. Or you can write the dfx dx. So this is a concept that we bring in, we repeat here, and actually it will be used a few times later on. So if you're looking at this relation, basically this term can be written as minus dqx double prime and dx. From there to there, based on a small change of a function divided by the small change of the variable, and then you can assume that the function is continuous and differentiable. Then we can get that one, and then the plus q dot and the rho c partial t. Right? So from here to here, basically that's just the math. Right? We don't have any physics being introduced. And then the next step, as we said, after we get the energy balance equation, it's a heat transfer problem, right? We will need to bring in the heat transfer rate equation. And that's the next step. So we bring in Fourier's law for the conduction problem. Fourier's law will replace this conduction heat flux. So we will have minus d dx minus k partial t partial x plus q dot, and that are the same. Yeah, I should write, now I should change everything to partial differential. and this should be partial differential as well, because it's not just the function of x. So this is the Fourier's law, just in the form of heat flux. Then we bring in here, and this two actually can be cancelled. So this is a equation that we derived for the x direction. So when we have the three-dimensional problem, every direction needs to be considered, right? Then add up together to give us the overall equation. So similarly for y and z directions, then we can get the partial x, k, partial t, partial x, and partial y, k, partial t, partial y, plus q dot equals to rho c partial t partial t. So this is the most general form that we obtained for this non-one-dimensional, non-steady, and considering the heat generation problem, right? So this is the most general format. And we don't typically dealing with this form in your calculation because that's too complicated. We're dealing with it in certain. We always simplify the problem in certain way, particularly in this subject. So in most cases, we're only dealing with one-dimensional problem, and sometimes we get rid of the heat generation term. Sometimes we get rid of the transient term, and in most cases, we consider k is constant, which means you can move the k out of the differential. But for certain problem, if it's saying it's not constant, then you need to keep it inside there, and for your calculation. All right, so that's all for today. Let's continue tomorrow.
I have some more questions.
Yep.
So while I was working on the assignment, in the saturated water table, there is enthalpy for fluid and gas and FH, which is evaporation, the enthalpy evaporation.
Okay. Yeah.
Where do I use it? HFG.
HFG is basically the difference between the.
Only difference between.
Yeah.
Okay.
Yeah. You don't use it. You don't use it because in your calculation you're either dealing with the saturated liquid or saturated.
Yeah, because for the other refrigerants such as the propane, they don't have the HFG, and only water one has one. So I was curious.
Yeah.
Thank you.
Can I ask a question about the assignment?
Sure.
For question 1, this is the TS diagram I drew. So 5 is where it comes out of the conductor. But is it right to connect it back to 1 and say that the pressures are equal?
So if you consider what happens in reality, this is your inlet, right?
Yeah.
Which is coming from air, which is atmospheric pressure. This is your exit, which is also connected to open air. I mean, there's a.
It should be the same pressure.
Yeah, it's same pressure. So, I mean, in reality, they are not directly connected because you are not connecting your exhaust gas to your intake, right? But when we're talking about cycles, we consider there is a virtual connection. So that's saying that the hot exhaust like dump the heat to the environment, then coming back